All right, good morning, everyone. Welcome. Nice cold day. Start with the joke today. It's a short one. Atheism is a non-profit organization. Because they don't have profits, because profits are religious.
Oh,
things.
yeah.
Non-profit. See?
Yeah.
They make you think, just like physics, same thing. Anyway. You all have your quiz due today, do that. The recitations, if you already have you're like, the same question was repeated like a million times. I fixed that for all future recitations. So that's all. And then, quiz today. I extended quiz 2 as well because we're finishing up today, so I don't expect you all to know all the things by Saturday. So I extended that to this Wednesday, and we will catch up. We will make up that one missed day that we kind of had. Last class, this is what we spent most of our time on, was setting up integrals. This is the process, and I updated this slide. The old one's still there, I'll point out in just a second. But this is the process that we do to build an integral. Solving it, ironically, I don't really care that much about, because making problems that you can actually solve the integral without spending a bunch of time, they're actually pretty difficult to make. So I just have you all kind of set up the integrals, and that's fine. Even if they're unsolvable, who cares? If you can set up the integral, you can have a computer do the integral for you. I made a few mentions down, actually, I wrote it here. So this integral is just an infinite sum. If you ever program an integral, some integrals can't be solved analytically, meaning you can't the integral of x squared is x to the third over 3. That's an analytical solution. It's got like an equation for it. Some are either impossible to solve or very, 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 very difficult. But every integral can be solved numerically really easily. And how does it compute? So numerically means the computer calculates it. What does a computer do to calculate an integral? Riemann sums. So Calc 1, the first thing you will learn, what an integral was, where you all through a bunch of trapezoids. And then if you added up all the trapezoids, it became an integral, it became the area of the curve. That's literally how you program integrals in a computer. You split the thing up into a million trapezoids and add them all together. And a computer can do that very easily. So every integral can be numerically solved pretty simply by that. Here's the integral. We replace dq with creating in spatial coordinates. We replace it with lambda times dl. We then replace dl with what is appropriate for us. So if our wire runs left to right, we replace it with dx. If our wire runs up down, dy. We're going to see the second one, the circular loop, today. I'm going to do that problem. So I'm not going to mention that yet. We'll see it when we see it. And then to solve the integral, you need to break into x and y components. How do you do that? You draw the angle, just like you all have broken things into any components. Boop, you draw an angle here, and if this was a positive charge, you'd make an electric field, and that angle is that angle, and you can do cosine and sine to get the components. And then you get everything in terms of known variables. So we did that whole problem. Yeah. Sorry, repeat that?
Are we only using lambda?
Yeah, so that's a great question. Are we only going to use lambda? I am not going to have you all solve this problem. I'm not going to have you all solve problems that are more than one dimension. So for this in particular, for Coulomb's law, the reason is, it's a great question. So we're only going to have one dimension, whether it's a line or whether it's a loop. And the reason is, if I made it a 2D surface, we'd have to do a double integral. And you all are learning about double integrals in Calc 3. They're really simple. A double integral is just exactly what it sounds like. It's 2 integrals. A triple integral is exactly what it sounds like. It's 3 integrals. But I'm not going to spend the time teaching you all how to do those in this class. This is sufficient. So if we had a 2D surface, we'd have to set up a double integral. If we had a 3-dimensional surface, we'd have to set up a triple integral so that we could get all the charge in those dimensions. So great question. We will use those. So what he's referencing, I mentioned lambda. What he's referencing is this slide where we had different charge distributions. These are going to be important for Gauss's law. We are going to work with multi-dimensions with Gauss's law, so these will be relevant then. You break things in x and y, and I worked through the whole problem, and it was a grand time, and I didn't solve the integral because it's gross. So real quick, today I'm not going to spend that much time on this. This one is ironically easier. You may be like, how You'll see why. This integral is actually very easy to solve. We'll do this one very quickly and then move on to Gauss law. Just doing one more example. Make sure you all can do these problems. Make sure you all can build an integral for the line of charge. Make sure you all can build an integral for the loop of charge. There's 4 problems in the problem set practicing this, 1 problem in the quiz practicing this. Your old recitation has one of these is going to be on the test. Whether the line of charge or the loop of charge, one of them. Make sure you all can do these. And it's not going to be just this. You'll see in the problem set they look different. So that's about as much as I can, try to convince you of that. Derive the equation for the electric field distance z above the center axis of a ray of charge with uniform charge density like that. So, what are we solving for? We are solving for the electric field at that point. That's what we're solving for. All this mumbo jumbo, all this wording, you need to make sure you know what you're solving for before you try to do anything else. The electric field at that point. Okay, what's causing an electric field at that point? This ring has charge on it. Let's just assume it's positive charge. And that positive charge is spread out all across that ring, everywhere on it. So how are we going to solve this problem? We're going to do that integral. E equals the integral of k dq over r squared. We can do it for 1 point charge. This adds up all the point charges together. Now, before we even do that, though, I'm going to add to my picture, because pictures are very, very, very important, and they're very, very, very useful. You're going to see as we solve this problem, if we didn't have this picture, if we didn't add things to it, it'd be very hard for me to convince you of various things. So one of the things that's useful is I'm going to pick a little dq here. Boom, there's my dq. And we're going to draw the distance from it to the point. You pretty much always want to do those 2 things. Pick a little dq, draw what r is for that little dq. Great. Now we're going to follow that process I told you all. We're going to first replace dq with lambda dl. This comes from the definition of charge density. If I multiply the charge density by a tiny little length, I get a tiny amount of charge. Okay, now we're going to write dl in terms of spatial, not dl. We're going to put it in terms of something else. And here's where this is going to be something that you might have seen in Physics 1, but this is very important for you to know. This relationship I'm about to write for you all is very, very important. It's called arc length. We're not going to use x, we're not going to use y, we're not going to use z. We're not going to use any of those because this loop does all of those, it does x and y at least. Something you all learned, hopefully in Physics 1, is that if I have an arc of something, wire, road, who cares what it is, and if it's a circular arc, and it has a length of s, that's like, it says, hey, I've got a road, I want to figure out its length, it's a curved road. If you know this angle, and you know this radius, it's a very simple relationship. S equals r times theta. Yeah, this is something you might have learned from Physics 1, maybe not, but it's a very important, it's a very useful relationship. And you're like, how does this make sense? This is something every single one of you knows for an entire circle. This theta is in radians. That's something important you need to know and we're going to see why. If this was an entire circle, S would turn into circumference. R would still be R. What is the angle for an entire circle in radians? Great, look, it's the equation for circumference. So like you can see, it works. If you had half of it, then instead of 2 pi, it'd be pi. If you had a quarter of it, it'd be, so it's really easy to prove that to you all. This is experimentally proven. This is not theoretical. This is literally, you can get a circular object, tie a string around it, and take the circumference, divide it by the radius, and you get 2 pi. It's just how the world works. That's where 2 pi comes from, experiments. Okay, so this is what we're going to replace dl with. So instead of s, I know it's going to look a little ugly, so ds equals r d theta. And if I wanted a tiny, tiny little piece of that arc, it would be the radius times a tiny, tiny piece of that angle. If I kind of drew that on this picture here, it's going to be hideous, but So there you go. There's my tiny, there's my R. There's that. So the punchline here is that when you have an arc, it becomes lambda times, in this case, it's a capital R, not a lowercase r. You have to use the radius of your circle. My radius of my circle here is big R. Don't mix them up. Use your picture to make sure you use the right variable. And so dq turns into lambda dl. dl turns into r d theta because of arc length. And just to show you all, just to connect this to that PowerPoint slide that I started you all off with today, look, it's kind of just written right here, but this is the reason why. If it's an arc, dl becomes r d theta. Okay, so continuing onwards, this becomes the integral of k times lambda r d theta over r squared. And now you can pick your favorite here. We can either break into x and y components, or we can get everything in terms of known variables. It's whatever you like better. It doesn't matter what you do first. I'll go ahead and replace the little r. I'll do that now. That's what I did last time. The order here doesn't matter though. Hopefully y'all can tell from this picture. So this z, I'll move it over just so it's a little bit more clear, because it's kind of gotten in the way of some things. Hopefully y'all can see that r squared equals capital R squared plus z squared. It's a triangle. You can see it's a nice little triangle. That's the hypotenuse. So we get, this is the integral of k lambda r d theta over r squared plus z squared. Fantastic. Okay? So I told you all this problem was easier than the last one. Here's why I'm going to show you why it's easier. K is a constant, lambda is a constant, r is a constant, z is a constant. Every single thing in this equation is a constant. So the magnitude of E, remember we haven't broken into components yet, so this is the magnitude, is going to equal K times lambda times capital R over R squared plus Z squared. The integral of d theta. There's only one last step we need to do. It's break things into x and y. Yeah, we haven't set the bounds, but it's a great point. Let's do it now. What are our bounds? You need to integrate over the whole circle. 0 to 2 pi. We do need bounds to this, and if you don't put bounds, then you can't actually solve it. Just turns into theta. This is not a half loop, this is not a quarter loop, it's a full loop. This theta I'm integrating over is around the entire loop to get the entire thing. Okay, let's get things into x and y. To get things into x and y, we need to draw an angle, and here's where you need to be careful. There's many times you need to be careful. The angle that we're considering, so look, here's our electric field. We need to break that into x and y. So here's a triangle. This, do not call this theta. Do not call this theta. Theta went around the circle. Theta went like on that plane, swept along that plane. This angle is not the same as the one that swept around the plane. Like, hopefully, theta is the one, I'll draw theta on here. Theta is this tiny little thing right here. That's theta. This is not that. Do not use the same variable for two things that are not the same thing. So this is where you all will see this in Calc 3. We use phi oftentimes. Phi looks a lot like theta. Theta, the little loop's at the top. Phi, the loop goes all the way to the bottom. That's at least how I draw it. Two different angles. If you put this as theta, then you're saying they're the same. They're not the same. It's wrong. It's bad. Don't do that. So that is phi. The Greek letter phi. I don't know, phi. And even I'll put this here. Phi does not equal theta. They are not the same thing. They look similar. They're not the same thing. So, to break things into components, you all can see my beautiful triangle here. To get the x component, it's going to be all this junk, k lambda r over r squared plus z squared times the integral. We're not going to integrate yet. Do not integrate until you have everything done, and then you can integrate. Times, in this case, it's going to be cosine of phi. Because to get the x component, in this case, it's the adjacent side, so you multiply by cosine of phi. What is the value of cosine of phi? Remember, equals opposite or equals adjacent over hypotenuse. My adjacent side is capital R. My opposite side is lowercase, or my hypotenuse is lowercase r. So again, I'm running out of room here, so I'm going to steal all this and move it to this picture. All right, so EX is going to equal K lambda R. And remember, R equals the square root of R squared plus Z squared. We already did that. So I'm going to go ahead and pull that out. So we're going to R squared plus Z squared to the 3/2. Because we had the original, and now we have a square root 1, and 1 plus 1/2 is 3/2. And then we get an extra R. So I guess we get an R squared now. And then we have the integral of d theta from 0 to 2 pi. And the final answer for that, this is... Okay, we do end up... Sorry. This one's a little unfortunate. I'm going to show you all why. Oh, how to... All right, so this one is... So this is how we would solve this, but I'm going to warn you all, there's something we kind of neglected here that's fairly important. So actually, this one we're not going to even solve. The x component we're not going to solve. I'm going to make it clear to you all. If you solve this, you need a non-zero value. Here's the problem. If you all look at your picture, I should have kind of done this to begin with. This is where sometimes the angle thing doesn't give us the full picture. It's kind of unfortunate. This x component is right here. Let's go ahead and remember, whenever we do these, it's actually useful to draw two of them. Here's this one's electric field. What do you all notice about their x components? What are they going to do? They're going to cancel. So actually the way I set this up was, yes, this is okay, but it's not perfect actually, because the x component will even be different depending on where you're at on it. I won't get into it too much. What you want me to know here is BC symmetry. Use that and don't worry about the math. In this case, what's going to happen to the x components? They're going to equal 0. This problem actually has all three dimensions. The x component, the y component, and the z component are all present in this for the electric field. If you're like, how is that the case? This electric field points out to the right. As you spin around the circle, the electric field spins around. So it has every single component, and we're not going to go through and calculate every single component because that's messy. So, in fact, we're just going to go ahead and say, boop, don't worry about that, it equals 0. Because if you do that integral, you don't get 0, and I'd have to get more into the math, and unit vectors would be a better way of doing this to prove that to you, but I'm not going to bother with it. So the x component is going to cancel, and this is where you have to start defining what directions are. What you want to decide, which way do you want up, down in this picture to be, y or z? I don't care. Y it is. The y component is the only one that's going to exist. The y component is the only one that's going to exist. The up, down. So if we go look at the y component, it's going to be all the same. K lambda r, r squared plus z squared, integral 0 to 2 pi, d theta. But in this case, we're going to use sine of theta. And this will be fine. This will work out for us. The problem with the x component is we have positives and negatives. Depending on where you're at in that circle, the electric field would point to the left or point to the right. And we would have to respect that in how we built the integral. We didn't do that. The y components all point up, so we don't need to bother with splitting things into x and y. Thank you. I made the mistake. See, it will happen to you too. When you go too quickly, you'll accidentally write thetas, or you should write phi's. And we're not integrating sine of theta. Yeah, thank you for catching that. So in this case, sine of theta is going to turn into phi is going to turn into z over lowercase r, which is going to turn into z over, square root of r squared plus z squared. And so we get that the solution of this is k lambda r times z over r squared plus z squared to the 3/2, integrating from 0 to 2 pi for d theta. That's just 2 pi. So my final solution is 2 pi k lambda r z over r squared plus z squared to the 3/2. And you might look at this and be like, that looks awful. But it's very easy to solve. This might look like, oh my gosh, so many variables. But that's really easy to plug into a calculator, honestly. That's really not that bad. It looks like a bunch of mess, but every step we did was actually pretty simple. It was all the steps we did where we replaced things with those variables. We just had to break it into components. There was no, the math here was simple. The math here was very simple. We didn't do any, like that integral is literally the easiest integral you could possibly do. Yeah. So remember that lowercase r is right here. Yeah, so it's the hypotenuse found from the triangle. Which, yeah, comes from, here, I'll highlight this. There you go. Yeah. Yeah, that's a good question. There is a third component, the z component, it's 0. If we define like out of the page and into the page as a component, that would be 0. So in this problem, I would just say, hey, what's the net electric field? If there only one component exists, that is the net. You don't need to do Pythagorean's theorem if the others are 0. So, I'll just jot that over here. E, z equals 0. All right. Another thing I want to mention this, whenever we work with these variables, we don't actually put units after our answer. We don't actually put units after our answer, and the reason we don't put units is the units are all kind of in here as well. So if you put the units and you still have the units in here, then you have double units, and that's bad. So it's another bit, I guess it's kind of nice with these variable things. We don't actually put units. What we would say, if I in a book or something like that, it would say this is the solution, and the answer would be in units of newtons per coulomb. But you wouldn't actually put newtons per coulomb after this. It's just a semantics thing. Okay, so there you go. Make sure you try these. Follow that recipe. That recipe is the way you solve them. The way that I made that recipe, that step-by-step list, is I found when I had students come in my office hours, I found I was guiding them through that exact process every single time. So to that end, when you all are working on this, if you're stumped, go through that process once. And if you get stuck, like if you're unsure how to do a particular step on it, that's fine. Come, look things up, come to my office hours, all that kind of stuff. But this is the process. You effectively want to understand this process, want to have it memorized, because sure you get the note card, but that's not going to exist in the final. So you do need to know how to do this, but at least for the first test and things like that, if you're unsure, you can write this down on your note card moving forward. You need to know how to build integrals. And every step here, for the most part, is something you've done before. You all know about density. Density is something you did in chemistry. All we did was use density. Except instead of an M, it's a Q. You all know to get things in terms of known variables when you're doing an integral. You all know that. And something else is changing you got to get in terms of the things that you're integrating. You all know how to break things into X and Y components. You've done that before. So it's just putting a bunch of pieces of things you know together. It's one thing. Yeah. Sure.
In the previous problem, we integrated sine and cosine together. How come this example not integrating cosine and sine?
Yeah, so this is a constant. The reason is this phi is a constant. Everywhere on this circle, it's the same angle. If we looked at this side, it's also phi. If you could look at this thing from the side, if I picked a thing here and you looked at it from the side, it would still be phi. And the reason is phi, if we write the relationship, z is a constant, capital R is a constant, z is everything in this problem is actually a constant. Every single variable in the entire problem is a constant. Which is why we can pull everything out. Yeah?
So the picture symmetrical is going to be 5?
So the tricky thing there is this picture was symmetrical as well, in a different way. If you have an arc like this, you sometimes have to define different variables. If you have two different angles at work, you need two different angles. One angle we swept around the circle, the other angle was how much is my thing. All right, all good questions. But yeah, try these out. As I've mentioned a million times, and will continue to mention a million times, the only way to learn this stuff is to do it yourself. Like, that is the best way. I wish there was a shortcut. I haven't found it. So, okay, Gauss's law. Gauss's law is going to be an entire PowerPoint slide showing you all a trick to calculate electric fields for problems that would otherwise be unpleasant. And then behind the scenes, Gauss's law is one of Maxwell's equations, which there's 4 equations in Maxwell and Pierce equations, and they describe all of electricity and magnetism. So like this entire course can kind of be derived from those 4 equations. I'll mention them at various times. We're not going to spend too much time on them, but Gauss's law is one of those. It's honestly, in a lot of ways, just going to seem like a math trick. It is going to have as involved, so like those Coulomb's law, where there was like, do this, then this, then this, then this. If we scroll to the very end of this, fingers crossed I put it here, if not yeah, there it is. Oh look, another step-by-step process for how to do this. This has many steps to it. So I'm going to help you all understand, I'm going to help you all understand all these pieces and why a lot of this PowerPoint is helping you understand the why and how to do it, and then this is just how to do it. This is the summary of how to do it. So we'll get to this at the very end. But what I am preparing you all for is that this is a multi-step process, and in a lot of ways it's kind of a math trick. But first, I'm going to try to convince you all of Gauss's law. I'm trying to convince you that it makes sense. We'll see how effective I am. Yeah, so we're going to talk about something called electric flux. Flux is going to be very useful when we get to magnetism. And if you don't understand flux, you won't be able to understand how generators work. So that'll be a future thing, so we're going to spend some time on it now because it's for this and for that. And then we're going to use Gauss's law and do it. So, electric field lines. So previously when we drew electric fields, we drew them as a bunch of different arrows. If I had a positive charge, I had a bunch of different separate arrows. They were all separate. Bigger the arrow, bigger the field, right? Another way you can draw these fields is you can connect them together into just, one big line. It's another way of expressing it. And how do you get the strength of the field? The closer the lines are together, the stronger the field. The closer the lines are together, the stronger the field. If you all look at my positive charge here, the field is the strongest close to it. Where are the lines closest together? Next to it. So it all matches what we've learned so far. So this is another way of showing fields. If we wanted to go back to the old way of drawing a bunch of arrows, you could do so. You would just draw tangent arrows. You would just draw a bunch of arrows that were tangent to it at every point. 2 different ways, exact same thing. They're arrows, but this is a useful way of expressing a bunch of arrows. Just, connected together into one big arrow. Okay. So that's the major idea here. You all looking at these pictures, we're probably like, this is fine, this is cool. I'm just trying to explain, connected to what you all learned before. Closer the arrow, stronger the field. That's an important idea. Keep that somewhere in your mind. All right. The more charge we have, the more lines we draw, because then they're closer together and it's stronger. Stronger field when you have more charge. Again, none of this should be a crazy idea. None of this should be anything like wild. It's just me trying to make sure you understand this notation before we start using it. You can see here we have a bigger charge, more arrows. Smaller charge, less arrows. Wow. Awesome. That's what you'd expect. Totally, hopefully intuitive. Okay. Here is the logic behind how Gauss's law came to be. This is one piece of it. So Gauss, had the first name Carl, middle name Frederick, found that if you draw a bubble around the charge, the number of field lines through the bubble is proportional to the amount of charge you have. The amount of field lines through the bubble gives you a sense of how much charge you have. This is purely based on this last thing I just told you. Let's draw some bubbles. And who cares what shape these bubbles are? It doesn't matter. There's a bubble, there's a bubble, there's a bubble. The more arrows that go through the bubble, specifically outwards or inwards, one of the things we will say is outwards is like positive, inwards is negative. If you go out through the bubble, it's positive. If you go into the bubble, it's negative. So they can cancel out. For example, if you all look at down here when you had a positive and a negative, if I drew a bubble here, I would get the exact same number of arrows out as in. So how much charge do I have? 0. Out is positive, inwards is negative. More arrows, either more arrows outward, hey, I got more positive charge. More arrows inward, I got more negative charge. Not a crazy idea. Like this is just coming from this. Okay. We call the number of field lines flux. The number of field lines that go through this bubble we call the flux. Flux is a fancy word, you don't see it like flow. How many are kind of like quote unquote flowing through it? If you ever talk about the flux of something, it's how much is changing, how much is kind of happening in the thing. That's one use of it. It's used in a lot of different ways, unfortunately. You all probably heard the word flux from like Back to the Future, where they just use it because it sounds sciencey. Another name for flux is you use it when you're soldering. Soldering flux helps you melt the solder. That's completely different. This flux is how much of something goes through it. So, for example, if you imagine like the flux of a river, that'd be how much water is kind of going through a certain area in a certain amount of time. You can think of it like a flow. These field lines aren't flowing, but this can help you if you think of it that way. Like a flow, if you imagine these arrows as like something flowing through it, that can kind of help you. Outwards positive, inwards negative. Out of the bubble positive, into the bubble negative. Flux. Okay. So, go ahead and do this one. What's the electric flux to the closed surface? So I have a positive and a negative charge here. I got a bunch of arrows and I do a random bubble. This bubble is not any specific shape. I purposely made it weird looking. Using the logic I just taught you, find the flux. Is it 16 newtons? And these are the units for flux. We're going to see why they're the units for flux in a little bit. Newtons meter squared over coulombs, negative 16 Newton meter squared over coulomb, 8 Newton meter squared over coulomb, or 0 Newton meter squared over coulomb. Try it out. There's only one right answer. Oh, my iClicker base. All right, I might have to reset things. All right, keep looking at it. I have to reset it. The physical base looked like it was connected, but it wasn't. So I'll reset this one, but keep thinking. I'll resend it out. Yeah, ignore that. I'll delete that one. It'll be gone forever. I'll give you all a whole minute. There is no map here. At most, you are counting. All right, 20 seconds. Okay. Is it showing up on everyone else's or no? Not yours. Yes, yours. Yeah. Okay. Well, that's weird. I'll leave it open a little longer. Maybe refresh it, close it, and reopen it. You know, classic. I'll just leave this open. If yours is not finding it, close it, reopen it. I'll just keep leaving it open when I talk about it. Okay. Flux. Two ways to answer this. One is the definition. Remember, Gauss said it's proportional to the charge enclosed. How much charge is enclosed here? If I have a positive charge and a negative charge, 0. 0 times a million is 0. 0 times proportional means I can multiply it by something. 0 times 3 is 0. 0 times negative 5 is 0. 0 whatever, it's 0. That's one way. The other way is the definition of flux. Outwards is positive, inwards is negative. So let's just, count how many are positive. I got 1, 2, 3, 4, 5, 6, 7, 8 going out. How many do I have going in? 1, 2, 3, 4, 5, 6, 7, 8. Positive 8 minus 8 is 0. Look at that, it all works. Yay! The flow, how much is going in, how much is going out? The same. This flux, you can almost think of like how many students are leaving a room and how many students are coming into the room. 5 students leave, 5 students come in. What was my kind of change in students? Nothing, 0. Kind of like that. Again, these things aren't technically flowing, but this is a useful way to conceptualize it. All right, so here's the fancy math way of expressing this. Flux, there's my symbol for it. This is capital Phi. So it's a circle, you put a line through it, and you give it some top and a bottom. That's phi, capital Phi. And it's E for electric flux, because we're going to learn that there's magnetic flux. In math, subscripts are adjectives. Subscripts are adjectives. So phi here represents flux. E means it's electric flux. We'll eventually learn that there's a magnetic flux. So we'll put a B instead of an E, because B is for magnetic field because of reasons. Okay. The electric flux equals the electric field dot product with the area. Dot product with the area. So it's how much electric field, how much area, and whether or not it's going in or out. That's why we have vectors involved here. We care about direction, outwards positive, inwards negative. And we care about how it's going out of it. That's something I kind of neglected to mention before, but if it's at an angle, it's not as much as if it was going straight through it. An example for this is when you blow a bubble, you blow dead onto that bubble. You don't blow it sideways. Yeah, so where's a wire? Grab one from my backpack. Alright, here's a nice HDMI cable. Attach to other things. Whatever. So, here's the idea of flux. We think of it like a flow. Here's my area. Here's my loop. You can do whatever, but here's a bubble. If I want to blow a bubble, I blow dead on. I put the wand in front of me and I blow dead on. If I blow it this way, where it's not dead on, I'm not going to get any bubbles. The angle matters. If I'm a little bit in between, I get a little bit more, but not as much as if I was dead on. Angle matters. That's the logic here. Angle matters. And we can see that here. Something that shows up here that you probably have seen before, but I might need to remind many people of, the area vector. The area vector is a vector that is defined as the vector perpendicular to the surface. So this table in front of me, if I wanted to define the area vector, the key to finding the area vector, it's really simple. Take your pencil and put the eraser on the table. The area vector points in the direction your pencil is pointing. That's how you find the area vector of any surface. And it is a vector that describes the surface very well at that point. So here's the example. Here's my table I just mentioned. You put the area vector straight up. If you have a curved surface, like my water bottle, you can do the exact same thing. Put your pencil on the curved bottle, and if you want the area vector at some point, just put your pencil at that point. And it points, in this case, radially outward. You all need to be able to draw area vectors. It's going to be a thing. The angle here is the angle between, so this is a dot product. You all are going to do dot products in Calc 3 a bunch. You're going to see them. I am not going to teach you how to do the dot products components-wise. It's actually quite simple. So if I wanted to do E dot A, the dot product of this would be the x component times the x component of the area plus the y component times the area of the y component. We're not going to actually do this in this class. I'm not going to have you do the math for this, but I'm just mentioning it it'll help you in your calc. This is mathematically how you do it. You break it into components, you do that. One way. The other way, and you all saw this in Physics 1, I know whether or not you might remember it, it definitely was there, it was with work. Work was the dot product of force and distance. And now I will try to convince you all what a dot product does, because this is something I wish someone showed me. It's multiplication. You can see it's multiplication. But it's doing something that's actually pretty simple to convey. It is the multiplication of the electric field magnitude times the area magnitude times cosine of the angle between them. Let me draw this. So let me draw a electric field pointed to the right, and let me draw an area vector pointed up. What's causing this? Don't care. If I want to do the dot product of these, there's my angle. I'm going to show you all what a dot product does using something you've already seen before. if I broke A into its components, if I drew a pretty triangle of A, I would get AY and AX. How would I get AX? A times cosine of theta. So what are you doing when you're doing a dot product? You're multiplying the parts of a vector that are parallel. You have two vectors. A dot product is just taking the 2 parts that are parallel and multiplying them together. That's what a dot product does. So if you all see that picture there, if I multiply, so E dot A equals EA cosine theta. Look, there's A cosine theta. There's E. This is what you're doing. You effectively find the component of one of the vectors that lines up with the other, and you multiply them together. That's a dot product. What does a cross product do? It multiplies the parts of vectors that are perpendicular to each other. So if you all remember work, if I want to find work, it was F dot D. If I push this desk to the right, I care about the force that's also to the right. That's why we found the parts that were parallel. That's a dot product. When you all did torque, you cared about the parts that were perpendicular because pulling on a rod doesn't make it spin. Pushing it perpendicular to it, that makes it spin. So anyway, whatever use that might be to you, that's the idea of a dot product and a cross product, at least for me conceptually. Dot products multiply parallel parts, cross products are perpendicular parts. And all the math is just doing that. Cool. Okay, so this is how we do it. The units, really simple. Where do the units for flux come from? They do have units. The units for electric field are newtons per coulomb. The units for area are meters squared. Multiply them together and you got the units. Newtons meters squared over coulomb. And like I said, the angle matters. All these pieces matter. How strong is my field? How big is my area? And is it flowing through it really well? Am I getting a lot of flow through it or am I getting no flow through it? Alright, hopefully everyone got the last one right at this point. Hopefully it was working. I think looks pretty good, like a good amount of people were able to. If not, let me know. Here's a new one. Electric field of 100 newtons per coulomb is shown. The electric flux through this piece of paper that has it's a square piece of paper with 2 meters by 2 meters. Find the flux. Is it 0? Is it 200? Is it 400? Is it none of these? Yeah. If there's ever more than one right answer, I'll give you a problem if you answer more than one answer. So, if you can only pick one, there's only one right answer. All right, give y'all 20 more seconds. The math here is trivial. It's really, do you know the angle? Do you understand flux? Can you find the angle? The right angle, the correct angle. All right. In 5, 4, 3, 2, 1. All right, so let's think of our bubble analogy. If this was like wind and this was a bubble, am I going to get a good bubble or a bad bubble? Good bubble. Good bubble. It's going to blow really, like a lot of these are going through it. I get a lot of flux. I get a lot of flux. A lot of this is going through this. All right, so we know the answer is not going to be 0. That immediately kind of rules that out. That helps us also figure out the angle. Basically, yeah, we got a lot of arrows through this thing. A lot of it are going through it. Let's just draw this. So here's my electric field. It's to the right. My area vector, it's an area it's perpendicular to the surface. So boom, it's also to the right. 90 degree to the surface. You could technically draw the area the other way, and this is where things get a little kind of like nitpicky, but we'll just take it generally in the same direction. Either the right A to the right. So flux, if we do the math, equals E dot A, which equals the magnitude of E times the magnitude of A times cosine theta. E is 100. A is 4. 2 times 2. Look, I'll write that here just to... And the angle here is 0. Cosine of 0 is 1. So this equals 400 with the units. If you missed this, that's okay. The reason I'm asking this is to help reinforce what flux is. Sure, I told you what flux is. That doesn't mean it makes sense. How do I make it make sense? I have you practice. All right, another one. Same problem, but now the thing is like lying flat. Now the electric field of 100, I have a plane 2 meters by 2 meters. I'll make it a little bigger because it's small for reasons that... We're only going to give you all a minute for this. Math is simple. Can you find me? All right, 20 more seconds. All right, in 5, 4, 3, 2, 1. All right, use our bubble analogy. This is going to not blow a bubble at all. No bubble, no flux. None of it's going through it per se. So how do we prove that mathematically? So the answer is going to be 0. How do I prove that mathematically? Electric fields to the right. Label your vectors. Get in good practice. Don't just draw arrows, label them. Otherwise you don't know what's what. The angle between these is 90 degrees. So if I do flux equals E times A times cosine theta, so 100 times 4 times cosine of 90, which is going to equal 0. Newtons meters squared per coulomb. Great, that's my flux. Cool. All right. Let's see. We'll do this next one maybe next class or something. It's at an angle. Can you be careful? We'll do that one next time. Okay. I am now going to show you this. We're not going to be able to spend too much. We only got 3 minutes, but I want to show it to you to plant the seed in your mind so that when next class we talk about it, maybe it'll make more sense. Remember the logic I told you. Remember what Faraday said. The flux is proportional to the charge enclosed. The flux is proportional to the charge enclosed. If we write that expression, the flux is proportional to Q enclosed. All right? There's Gauss's law. Here is flux. Now, I know it's an integral. That's because an integral is a better way of finding, like it's adding up all the fluxes if it wasn't all lined up nicely. So an integral does that, but it's basically the same thing we did. This is basically the same thing as EA cosine theta, E dot A. It's just more rigorous. Proportional to the charge enclosed. That's Gauss's law. It's the mathematical expression for those words. And proportional, what's the proportion constant? Epsilon naught, which is a new number. It's 8.854 times 10 to the minus 11. There it is. It's a number. Proportional means you multiply or divide it by something. That's what we multiply and divide it by. Experimentally determined. All right, so then we'll be just using this next class. That'll be the gig. How do we use this? Why is it useful? What's the point? That's what we'll figure out next class.
Thank you, bud.
Yeah, we go.